Dear participants, welcome back. The first presentation after the break will be delivered by Dr. Tetsuya Ishikawa, Director of RIKEN Spring 8 Center. He will present two light sources, Spring 8 and SACLA. So Dr. Ishikawa, please.
Thank you, Ichioka-san, and good morning and good evening. I'm Tetsuya Ishikawa, the Director of RIKEN Spring 8 Center. Today, I'm talking about the relation between synchrotron radiation facilities and societal goals. As you know, synchrotron radiation is a super intense short wavelength electromagnetic wave, which is an essential tool to explore the nanoscale world. Observation and manipulation of the nanoworld are crucial for various current nanoscience and nanoengineering, particularly for high-tech industries. Therefore, the social expectation for synchrotron radiation is high. Oops. Okay. The social expectations for synchrotron radiation facilities are expanding for these years. For example, social expectations for Spring 8 at the inauguration in 1997 were primarily scientific excellence and industrial applications. Major stakeholders were innovators and early adopters from the academy and industry. Only the Science and Technology Agency from government, now the MEXT, and taxpayers who considered benefit of the domestic society. But now, in addition to the scientific excellence, my movie is not moving so that I will proceed, but now in addition to scientific excellence and industrial applications, society expects Spring 8 to contribute SDGs, green innovation, social resilience, and even COVID-19. Stakeholders are increasing accordingly. A crowd of early majorities and late majorities have entered academic and industrial communities. Additional governmental sections, including economy, health, finance, social infrastructure, and police appear as the stakeholders. Taxpayers now start considering the benefit of the global society in addition to the domestic society. Okay, we have broad societal goals as exemplified by the Sustainable Development Goals. And photon science has the excellent capability of providing solutions to approach almost all SDGs. Here we show a worldwide distribution of accelerator-based photon science research infrastructures. You can find there are so many accelerator-based photon science RIs around the world. It is because these RIs are supposed to respond to different social expectations of each country or region. The expectations are often related to widespread industrial and economic activities. The photon science research infrastructures have high adaptivity to a wide range of existing and emerging problems. Since we have many different photon science RIs worldwide, it is natural to have collaborations and competitions. Research infrastructures have many common problems in primary accelerators, optics, detectors, and control technologies, so that various collaborations emerge among facilities. Here I show two examples. One is the three-way collaboration among large third-generation synchrotron radiation facilities. It started among ESRF, APS, and Spring 8, and Petra 3 joined later. The other one is a five-way collaboration among hard X-ray FEL facilities. Both collaboration holds collaboration meeting every 18 months, discuss common technical problems, and initiate collaborative R&Ds on various topics. From now on, I'd like to inquire about some concrete examples based on the case of my home ground, Spring 8. The name Spring 8 came originally from super photon ring HEB, but now many people consider it comes from solution providing ring HEB or solving problems ring HEB. It started user operation in 1997, approximately a quarter century ago. In 2018 fiscal year, we had accepted 2,261 experimental programs. Approximately 20% of them were from industry. We counted 17,000 user visits in the year. Total user visits from the inauguration in 1997 are approximately 300,000. It is the largest shared user facility in Japan. Now, recently, we compared the achievement of Spring 8 and SACLA by relating to 17 SDGs. We found that each of 280 latest press or least achievement connected to 3 goals on average. From this fact, we can say that the photon science research infrastructures are indispensable for accomplishing SDGs in 2030 and may be crucial to the carbon neutral in 2050. Now, let me show you 2 examples of activities toward a sustainable society. The first one is the development of various kinds of catalysts. Among them, carbon fixing catalyst and water splitting catalyst by using solar energy are of particular importance. These chemical reactions called photosynthesis have been proceeding in plant leaves for millions of years. Recently, we determined the atomic structure of the enzyme called photosystem 2, responsible for water splitting using X-ray diffraction at Spring 8. After that, we revealed the chemical process of water splitting using light energy with ultra-fast X-ray pulses from SACLA. We can use these data when we design artificial photosynthesis catalyst. The second example is a contribution to the fuel cell design. Fuel cell stack for Toyota Mirai was designed based on the observation at Spring 8. In the fuel cell stack, the chemical reaction of hydrogen and oxygen generates electric power, which rotates the driving motor. For the high efficient operation of the FC stack, it is necessary to discharge micron-sized water resulting from the chemical reaction. Determination of the shape of the efficient water flow channel strongly demanded non-destructive observation of micron-sized water. Toyota Motor Company observed the water and the FC stack during operation and ascertained the most efficient shape for the water discharge. Now, I understand the synchrotron radiation facility built in Korea is fourth generation facility. And although Spring 8 as third generation facility, we plan to upgrade to the fourth generation shortly. The characteristic feature of the first generation source is the small electron beam emittance. The line-shaped electron distribution and the beam for the third generation source shrinks to a point-like distribution. The number of electrons is unchanged so that we can get more brilliant light. We can use smaller vacuum duct with smaller electron beams and more miniature electromagnets to keep the electron orbit. Since smaller magnets need less electricity, we can use air cooling to replace the present water cooling. In total, the energy consumption will reduce to 2/3 of the present value. Brighter X-rays can spread up to research and development, speed up the research and development, enable 10 times data production efficiency. Undulator spectrum shows less tail peak, which makes it easier to utilize pink beams. As I mentioned earlier, as society's expectations for synchrotron radiation are rising, the number of users will increase, and the quality of users will change. The majority shift from those who want to use synchrotron radiation to those who want synchrotron radiation data. The market designs new product and improves existing product at customers' request and manufactures them from which product and manufacturing technology are born. The product repeats the cycle of collecting data for evaluation, analyzing it, and moving toward new design and improvement. It is the innovation cycle. Brighter X-rays increase the angular velocity around the innovation cycle and reduce the time for developing product and production technology. In addition, we can obtain a large amount of data quickly. We can adopt advanced and more accurate data evaluation, such as big data analysis using AI, artificial intelligence, which will lead to advanced design and improvement processes. Okay, we have 9 storage rings for synchrotron radiation currently in operation in Japan. UV Sol, New Swell, and 3 small rings cover the low energy region. Photon Factory and Photon Factory AR at KK cover the medium to high energy region. These 8 are all second generation facilities. Spring 8 is the only third generation facility covering medium to high energy regions. Now, many countries have developed medium-sized third generation synchrotron radiation facilities, causing the declining competitivity of Japan in the medium energy region. Therefore, we are currently constructing a 3 GeV fourth generation facility in Sendai to recover the competitiveness. We also plan to strengthen our competitiveness in the high energy area by making it the fourth generation. We know that the renovation programs are ongoing at our competing facilities. Among the member facilities of the three-way collaboration, ESRF in France completed the accelerator renovation in 2020. The APS of the US is completing the renovation in 2024. Both renovations cost approximately 800 million United States dollars. In addition, Petra 3 in Germany is also planning a renovation, and China is constructing a new fourth generation high energy synchrotron radiation facility, HEPS, in the suburb of Beijing. The large-scale synchrotron radiation facility have opened up the high-energy photon science. The high-energy photons, in other words, X-rays, unravel the mystery of many substances from the atomic level. We know many phenomena, how they happen, but don't know why they happen. To know why is the first and essential step of innovation. And, the renovation towards Spring 8.2 will significantly reduce energy consumption, but aim for the highest performance in the world. We will adopt multi-band achromat MBA technology to achieve ultra-low electron beam emittance. A significant development is how to keep the simultaneous high stability. We use short period undulators investigated both in Spring 8 and SACLA, and we use the SACLA's LINAC for the injector. These lead to a significant reduction in energy consumption. Even if we reduce the electron beam energy from the current 8 GeV to 6 GeV, we can cover the same photon energy range as the current one by using shorter period undulators. In addition, the use of permanent magnets for bending magnets will reduce power consumption. Shutting down the booster synchrotron injector will lead to an additional reduction of power consumption. On the other hand, we will promote bright high-energy X-rays in performance after significantly improving brilliance. We will keep the stability of beam performance to the highest level. These are made possible by the high level of experience in building Spring 8 and SACLA and the high level of technology and accelerator elements of Japanese private companies. Such renovations are in response to the expanding demands from society. Synchrotron radiation supports science and technologies today and opens up tomorrow. We will convert Spring 8 to 100 times brighter Spring 8.2. For the conversion, we will create new technologies if necessary and advance the existing technologies. The conversion established a cutting-edge research base that contributes to the development of society because the new facility will be a more vital solution provider. It provides a scientific and technical basis for solving various issues that contribute to the wealthy life, good health, and longevity, and safety and relief required by society. One example is the application to social infrastructures. We haven't applied synchrotron radiation to this field. However, since this field consumed many resources, the integration of slight improvement results in the considerable saving. We can evaluate the cost of process with scientific or technical rationale. What synchrotron radiation can do for this field are contribution to deterioration and break of structural materials, deterioration and break of the road pavement, reliability evaluation of new processes, energy-saving processes, anti-corrosion and rust prevention, and minimum life cost. Now, energy and environment are big issues for the sustainable future. They are the main target of green innovation. We have already mentioned the photosynthesis catalyst and the fuel cell stack before. However, what synchrotron radiation can do for this field extends broader and more profound. We have many items to develop and recyclable energy region, including solar cells and photocatalysts. We have many things to do toward hydrogen production, hydrogen infrastructure, and hydrogen applications, including fuel cell, toward the hydrogen society. Another critical target in this field is carbon recycling. We should convert carbon dioxide from industry to fuel, materials, and food with chemical engineering. For nuclear energy, JAEA is using Spring 8 for the preparatory studies toward Fukushima decommissioning. Okay, when I entered the synchrotron radiation business 40 years ago, I realized one observation by myself is better than 100 of learning. However, only observation is not good, but we need to use our brain. When consideration is better than 100 of observation, and next, one action is better than 100 of consideration, and one result is better than 100 of actions. Finally, many results lead to your happiness. And I believe the synchrotron radiation should be the light that make all you happy. And thank you for your attention. And the last slide, I'd like to show the specification and the contact to the facility. And you can find many websites that you can access to our facility. Thank you very much for your attention.
Thank you very much for the presentation with concrete examples of applications and with a somewhat philosophical ending.